So, welcome back, students. We will be again catching up with linear bounded automata in the second lecture. Okay. So, before going into the details of what linear bounded automata is, let's see that. In our previous lecture, we have seen that there are various classifications of Turing machine, but the point that I had focused upon is that whatever may be the change or whatever may be the modification that has been done for a Turing machine, the power will remain same. Okay, so the power will remain same. That is, power cannot be enhanced. That is the thing. Okay, but can the power be limited or restricted? So in the previous lecture, we have only seen the instances where the power cannot be increased even after modifying the Turing machine. But students see, we can actually, or we do actually have the option of restricting the power of Turing machine in various ways. Okay, so we'll see how can we do that actually. We can actually restrict the Turing machine, restrict the power of the Turing machine rather by changing certain aspects of the tape. So, firstly, see, we can actually take a non-deterministic. See, whenever we will be talking from now onwards, we will always consider a non-deterministic Turing machine. Okay, make this point clear. So, okay. So, we can actually limit a non-deterministic Turing machine such that the tape is used as a stack. Okay. So, what is the property of a stack? We are actually pushing an element which actually goes to the top of the stack, and again we are popping the element from the top of the stack as well, right? So we'll consider the tape to function like a stack. That is, the read write head will actually point to the top of the stack, and we can actually modify the elements from that top of the stack, or we can actually do anything considering that the read write head is at the top of the stack. Okay, and this will actually result into the realization of a non-deterministic Turing machine into a PDA or a NPDA, push-down automata, or maybe a non-deterministic push-down automata also. So as you can see, we are restricting the power because obviously by now we know that a PDA is less powerful than a Turing machine. So we are limiting some aspects of the tape, and we are changing the functionality of a Turing machine into a functionality of a PDA. Next, see, again, we are taking a non-deterministic Turing machine, and we use a finite number of cells in the tape. Okay, so we are limiting the number of cells. We are having a particular memory for the tape, and then we can say that the non-deterministic Turing machine will work or function as a finite automata. Why? Again, try to understand, we are specifically taking a finite number of cells, a finite number of storage, countable, which is countable. Therefore, this NTTM or non-deterministic Turing machine will act as a, or function as a finite automata. Okay. Now we are ready to move to a linear bounded automata. So let us give a casual definition of linear bounded automata. So the Turing machine is restricted. Again, a non-deterministic Turing machine. Sorry, I have not written. You all please check the point that the non-deterministic Turing machine is restricted in such a way that it can use the tape, but only the part of the tape in which the input is present. This is known as a linear bounded automata. Please, students, don't get confused with this second point where I had said that NDTM can use a finite number of cells. Here we are specifically or forcefully finiting or restricting the number of cells, and it acts as a finite automata. But for a linear bounded automata, it can change according to the size of the input, because see, what is written over here is it can only use the part of the tape in which the input is present, and this size of the input will obviously vary. We can have AABB, we can have AAABBB, we can have anything depending upon the language concerned. So the only restriction is that the tape can function in the area that is bounded by the input symbols, not towards the left of that or not towards the right of that. Okay, this is the main point. This is restricted at both the ends. Let us go into a formal definition a bit. So LBA or a linear bounded automata can be formally defined as M is equal to, you can see the entities quite clearly, and I hope these particular entries are already known to you, because in our first lecture of Turing machine I had described each and every entity separately. Okay, so they have the same meaning as that you have studied in the standard Turing machine definition. The only difference, see over here, if you look at this carefully, what I've written is all symbols of same meaning as in the basic model of Turing machine, with the difference that, see, two extra tape symbol exist here. This one and this one. Okay, this dollar and this C hash are two extra symbols that have been used in this linear bounded automata. So this C is actually the left delimiter, or it is delimiting the left part of the Turing machine tape, and the dollar sign is the right hand marker or right hand delimiter, which is actually marking the or constraining the right portion of the input tape. Okay, so again we can have the diagram for a linear bounded automata, as you can see. So this is the tape, and you can see the delimiters are there for this input tape, the two delimiters in the left hand side and right hand side. Supposing we are having n cells, this is a finite control, this is the read head. See, it is written read head, our head moving to right only. Again, another constraint, students. Here we are considering that this what should I say, this read head can move only to the right hand direction. Okay, and this is only R head, not read right head. Okay, we will see like why we are only writing R head, because this is a input tape. Okay, and we have a working tape over here, which is the actual tape that functions for the linear bounded automata. For this we have a normal read write head. Okay, since this was only read head, this is a normal read write head. Here we do not have a delimiter, we have a k across n cell, and k is a particular constant specified for each LBA. Okay, so for particular LBA designing, the one who is designing the LBA is actually supposed to define this constant k. Okay, so for this working tape, so this is the input tape, this is a working tape. For working tape we have k in cells, we have a read write it, and can move in any direction. I have also written for your convenience, one is the input tape, only rightward movement allowed and read operation allowed. Working tape, modify the contents in any way without restriction. Okay, there is leftward, rightward, any modification, whatever is allowed. Okay, so this is basically the diagram for your linear bounded automata, and as you can see, these both are the delimiters, and the function, whatever the linear bounded automata is functioning or working, will always work within these two delimiters. Okay, so coming to the power of a linear bounded automata, a linear bounded automata is a less powerful than a Turing machine. Yes, as per power is concerned, LBA is less powerful than a Turing machine. So again, we have some example strings or languages that are accepted by linear bounded automata. A to the a to the power n, b to the power n, c to the power n, which we already know can never be accepted by a PDA, but it can be accepted by a linear bounded automata. Obviously, it can be accepted by a Turing machine, but it can also be accepted by a linear bounded automata. Again, another significant point about linear bounded automata is it can accept null string. But if you remember, Turing machine cannot accept null string. This is a very major difference between Turing machine and linear bounded automata, which you should remember. Okay. Next, students, just for your reference, I have given a list of languages which are actually accepted by a linear bounded, or which can be accepted by a linear bounded automata. I'll just read this simply. A to the power n, b to the power n, c to the power n. You have already seen a to the power n factorial, a to the power n where n is a perfect square, a to the power n where n is a prime, concatenation of w to the power n, and w reverse. That is this is w, this is the reverse of w, and in between we can have anything. Okay, so all these languages are actually, this is just for your general knowledge, you can remember at least one or two or three examples out of this, that these are the set of languages that can be accepted by a linear bounded automata. Now, as for linear bounded automata is concerned, you actually need not go into major details of it, just the definition. Already I have defined it over here, the formal representation, the diagrammatic representation, the power comparison, everything is covered. So these are the basic things you need to know about a linear bounded automata. That's it. Okay, so thank you.